Welcome to the Explainer. Whenever we look at a massive highway cutting straight through a mountain or a sleek new roadway winding through a valley, it's remarkably easy to focus entirely on just the asphalt. But the real engineering marvel? It's the invisible, highly precise mathematical grid resting just beneath it all. Today, we're unpacking the complex earthwork equations that make modern infrastructure even possible. We're talking about the hardcore logistics, the complex algorithmic models, and the heavy maths required to literally move the Earth.
So this brings up a staggering logistical reality. How do engineers actually know exactly how much dirt to move to make a road perfectly flat? Because when you're carving a path through natural terrain, you're dealing with an incredibly chaotic environment, and the financial and structural stakes, they are absolutely massive. A miscalculation of elevation by just a few centimeters across a 10-kilometer stretch translates to thousands of unnecessary truckloads of material. That means millions of rupees in wasted fuel, enormous delays, and potential structural weaknesses. Modern engineering has evolved way past manual surveying. To tackle this massive scale, experts rely on highly systematized data models to perfectly balance the Earth right beneath our tires.
Section 1. The core objective. Systematizing earthwork analysis. To really get a firm grasp on this core objective, we need to look closely at the raw, structured inputs that civil engineers rely on to actually map out a site.
Before a single excavator even fires up its engine, the route is divided into standard intervals, usually every 20 or 30 meters. This is what we call station data. Now, this station data feeds directly into software algorithms to manage two foundational states, cut and fill. Cut refers to excavation, basically areas where the natural terrain is too high and a certain volume of earth has to be removed. Fill, as you might guess, is the exact opposite. These are valleys or dips where material needs to be brought in and compacted down to reach the desired road elevation. The ultimate goal of systematizing all this? It's called mass haul optimization. The algorithms analyze the station data to ensure that the earth cut from a hill is efficiently transported to fill the nearest valley. If the maths is totally flawless, the project balances out beautifully, drastically reducing the need to haul dirt away or go out and buy external material. It's really a highly choreographed dance of volume driven entirely by data.
Section 2. The bump in the road. When the ground changes unexpectedly. The catch here is that real-world terrain is relentlessly nonlinear, and that introduces a rather massive headache for these systematized models.
Think about the exact technical roadblock that can throw an entire project way off budget. Imagine you're plotting a highway. At point 1, your station data dictates a cut condition, meaning the ground is high. Then, 20 meters down the road at point 3, the next consecutive station, the data requires a fill condition because the ground is low. The critical vulnerability here is point 2, the unknown ground level change. Somewhere in that physical gap between the two measured stations, the terrain crosses the zero elevation line. That's the exact spot where cut transitions into fill. If a software program simply shrugs and assumes a straight, uniform slope between those stations, it's going to calculate a highly inaccurate volume of earth. And over kilometers and kilometers of roadway, missing these transition points leads to massive compounding errors. We're talking about ordering thousands of tons of fill you don't actually need, or seriously underestimating the excavation time required.
Section 3. The mathematical solution. Finding the transition point. So let's break down exactly how modern algorithms isolate this crucial zero-point variable without resorting to dangerous, expensive guesswork.
This methodology right here is the absolute technical heart of the project. Step 1 is where the heavy mathematical lifting really happens. The software uses complex interpolation, often nonlinear or polynomial equations, to determine that intermediate transition point based on the surrounding topographical data. It basically pinpoints the exact coordinates of the zero line. Then, step 2 is vital for accuracy. The program splits the geometry right at that transition point, creating totally independent boundary conditions for the cut and the fill. Now, you might be wondering, why is this separation so absolutely necessary? Well, because if you try to calculate volume across a zero point using standard trapezoidal rules, you actually create a mathematical void that drastically underestimates the amount of earth. Moving on to step 3, the software applies precise integration, often using the prismoidal or average end area methods, directly to these segregated portions. And finally, in step 4, the algorithm compiles all this dense geometric data so it can be presented visually, bringing all those raw numbers into a usable, human-readable format.
That final step, it's a complete game changer on a busy construction site.
Transforming raw calculation data into clear, graphical presentations bridges the gap between a highly complex computational model and practical, boots-on-the-ground execution. Look, a raw spreadsheet of X, Y, and Z coordinates can easily hide massive anomalies. A site manager probably isn't going to notice a mathematical error buried on row 4000. But a 3D graphical representation? That instantly highlights impossible slopes, erratic volume spikes, or erroneous transition points. It basically allows engineers to visually verify that the cut-and-fill balance is practically sound well before millions of rupees are committed to moving actual dirt.
Section 4. The final polish. Current project status. With the core interpolation models and volume integration protocols successfully established, the engineering team has now entered a crucial new phase of development.
Because let's face it, a brilliant algorithm is practically useless if it can't be deployed seamlessly in a high-pressure environment. That's exactly why the current focus is entirely on software refinement. First up, they're actively improving the graphical representation, ensuring that the 3D visualizations accurately reflect really complex geometries, things like spiraling curves or super elevations on modern highways. Second, enhancing the user interface is absolutely critical. Reducing friction for civil engineers who are working on tight deadlines means designing a tool that is intuitive, fast, and responsive. Finally, the team is heavily engaged in rigorous debugging of the program. They are stress testing the math against extreme edge cases. Think about what happens when a road transitions from cut to fill right in the middle of a sharp, banked interchange. Ensuring the software holds up under these incredibly complex scenarios guarantees that the systematized method will operate flawlessly out in the real world.
Which brings us to the end of our deep dive today. The engineering we rely on is vastly more complex than just the smooth tarmac we see on the surface. Every single inch of our infrastructure is supported by rigorous station data analysis, complex volumetric integration, and brilliant software design calculating the perfect balance of Earth. It's a fantastic reminder of the hidden maths that shapes our physical world. So the very next time you glide effortlessly over a newly paved highway, ask yourself, how many millions of invisible mathematical transition points are you driving over right now? Thanks for joining me for this explainer. Keep digging into the data, and I'll catch you next time.